Today we are going to take care of those concepts. Firstly, the seismic design for the new buildings and seismic design for the existing buildings as well, and base isolator and dampers. And also we will see the mass and damping related features in MIDAS Gen, and also nodal analysis and fiber analysis briefly. As many of you knows, we provide the webinar twice a month. First one is the general information of MIDAS Gen, and the other one is advanced feature, such as the dynamic procedure and column shortening, and also seismic design. So this month's advanced topic is the seismic analysis and design feature. And also next month we will have the same webinar for the general introduction and design procedure for the advanced topic. Before we go to the details for the seismic related features, I would like to explain about the general features of MIDAS Gen, because some of you are very first time for the MIDAS Gen. This slide shows the main feature and strong point of MIDAS Gen, which is seismic specific functionality. We provide the static seismic loads and response spectrum analysis. Also, linear and nonlinear time history analysis is possible. Also, base isolator and dampers we will see. Also, we are going to see the pushover analysis and fiber analysis. And based on those results, we can do the capacity design, which is the strong column with beam design in American standard. And apart from those, also MIDAS Gen has capability for the comprehensive design code. We can perform the design for RC structure, steel, SRC, and footing, and plate, slab, and wall elements, and also capacity design. As you can see here, we implemented the international design code, and also we are continuously updating and adding new codes as well. Also, MIDAS Gen provides the high-rise specific functionality, so we can fully consider the time-dependent material during the construction stage analysis. And then, based on those results, we can check the 3D column shortening results. And finally, even though we are considering those high-end analysis, but most important thing in MIDAS Gen is easy to use. So we provide the useful features for the intuitive user interface. Those functions would be introduced in the next month's the general feature webinar as well. So let's go to the seismic design for the new building. This flow chart shows the seismic design procedure as per the Eurocode for new buildings. For the new building, those procedures are required for the designing the building. Firstly, defining the performance requirements, and then ground conditions, seismic action, and load combination would be determined, and also structural regularity needs to be checked in order to determine the analysis method, and then perform the seismic analysis and also perform the safety verification, and finally perform the capacity design and also provides the detailing as well. So let's see the step by step. Let's start with the performance requirement. Performance requirement is the structure in the seismic region shall be designed to meet the proper performance requirement. So performance requirement is divided into two parts, as you can see here. First one is no collapse, and the other one is damage limitation. So it is different to the return period of seismic load. For the no collapse, the structure should not have the limitation of the collapse, And in terms of the damage limitation, structure should not have the limitation in use. That is the performance requirement. And in order to satisfy those requirements, the following limitations should be checked, which is the compliance criteria. So you can see what we need to check in terms of the ultimate limit state and damage limit state. For the ultimate limit state, we need to check the resistance and energy dissipation capacity. And also, in the global level, we need to check overturning moment and sliding failure. In terms of member level, we need to check the plastic rotation for the ductile component, and also we need to check resistance in terms of the brittle component. And for the damage limitation, we need to check the interstory depth as well as the limitation, resistance. And for the ground condition, in order to determine the seismic action, we need to specify the ground condition first. For the ground condition, the appropriate ground condition should be provided to consider the influence of local ground condition on the seismic action. So following tables are provided. And after determining the ground condition, and then we determine the seismic action. For the seismic action, there are two things we need to consider. First one is seismic zone. The other one is representation of seismic action. So if we see the details, firstly, the ground acceleration. Based on the local hazard, the national territory is subdivided, and then those reference peak ground acceleration would be determined, which is AGR. And also, for the important structure, the topographic amplification effect should be taken into account, which is the gamma R in this equation. Those important factor, based on those two, we will determine the ground acceleration for the seismic action. Seismic action's representation can be determined between those two. First one is response spectrum, and the other one is time history load. After that, we will determine the combination of seismic loads. MIDAS provides the auto-generation of those seismic loads. If we look at the program, we can automatically generate the load combinations. For example, if we click this auto-generation button, and by specifying those design code, and then program will automatically generate the load combinations, as you can see here. And when we generate the load combination, we can consider the orthogonal effect of seismic load, which means if we select the 130 rule, the 100% of the seismic load in one direction, and in the other direction, only 30% would be considered in the load combination. So using those methods, we can consider the orthogonal effects of the seismic load. After determining the load combination, and then next step is the criteria for the structural regularity. By defining the structural regularity, analysis method would be changed between those four. Lateral force method, which is using the static seismic load, and modal response spectrum analysis, and the other way is pushover analysis, and finally the inelastic time history analysis. MIDAS provides all those 4 analysis methods, and as you can see in this table, we can determine the structural regularity in terms of the plane and elevation. So based on those, your standard will give you which analysis you need to perform. And then we will perform the seismic analysis, which was determined in the previous step. Based on these seismic analysis results, we need to have the safety verification. Safety verification can be divided into those 2. First one is ultimate limit state. The other one is damage limit state. For the ultimate limit state, resistance will be checked, and also the global and local ductility and equilibrium condition, which is the overturning moment and sliding failure, and those factors are checked. And for the damage limitation, we need to check the story drifts for each different story. By doing the safety verification, and then we finally perform the capacity design. Capacity design can be called strong column weak beam design as well. Before we perform the capacity design, firstly, I would like to explain the concept of the capacity design. In order to prevent the brittle failure or other undesired failure, the proper design action effect needs to be provided based on the required ductility level, as you can see here. So if the ductility class is DCL, which means the low ductility, in this case, we can just use the general design, concrete design code, not the seismic design code. And if we determine the ductility class as a medium ductility or high ductility, in this case, we will perform the seismic design. And the design force would be differently defined based on those ductility class. And the concrete buildings are classified into the following systems: frame system, dual coupled wall system, so on. And based on those structural type, the behavior factor would be determined. Behavior factor is the factor used for the design purpose to reduce the force obtained from the linear analysis. Since the real structure is the plastic nonlinear, so in order to consider this property, we need to have this behavior factor. And in MIDAS, we also provide those concepts as well. If we go to the concrete design parameter and design code, you can see the dialog box here. Firstly, we will specify the design code among those. I will select the Eurocode 2. And then if you do not need to perform the capacity design, I mean the seismic design, just check off this option, apply capacity design. And if you need to perform the seismic design, check on, and you can see all those options. Here we can specify the ratio for the strong column weak beam ratio. So the design force of the column would be always 1.3% larger than the beam's resistance. And we can also change this ratio as well. Ductility class that I just explained can be selected among those. And based on this selection, you can see the factor for the shear force is changed, which is called gamma RD in the Eurocode. And for the some other structural member, which is the sub-beam or some other structural member, we can specify them as the secondary seismic element. Then program will not perform the seismic design for those selected structures. Also, we can consider the beam column joint design. If we go to this button, we can see another dialog box. Here we can see the structure type that we just checked in the table. So based on this selection, program can automatically calculate the behavior factor. Or if the user needs to directly enter this factor, we can also specify the factor here as well. And also the response spectrum function would be used to determine the wall detailing. Then after having this, after defining those factors, then we can perform the design. Go to the design, I see strong column weak beam design and ductile design. So for the beam and column, the results can be displayed in this table. If we see the beam design results first, results can be checked in the graphical report as well as the detailed report. Firstly, let's see the graphical report. So program provides this cross-section picture for the I end, middle, and J end. And we can check the design results based on those determined reinforcement. Also, we can see the ratio between the design moment and strength. For the shear design, the same. We provide the shear force and shear resistance, and then determine the rebars can be checked. So this using this graphical report, we can simply easily check the design results for each different member. And also, if we need to see the detailed calculation, we can use the detailed report. The detailed report will be provided in the text format. And you can see which parameter is used for the design and determine the load combination and design force and neutral axis, and all the results can be checked for the positive and negative bending moment, and also the shear capacity as well. For the capacity design, it needs the different rule to determine the design moment and design shear force. Firstly, the basic rule is strong column and weak beam. So column's failure, before the column's failure, beam's failure should be always first. In order to satisfy this rule, when we determine the column's design moment, we use the beam's resistance. So it means column's failure will be always later than beam's. Also, it is same for the shear force. Shear failure would be, before the shear failure, the moment failure should be performed first. In order to satisfy this rule, also we use the moment value to determine the design shear force. So you can check the detailed equation here. For the walls, in order to determine the wall design moment and shear force, firstly, we need to know the system, if it is wall system or dual system. And also, according to its shape, scat wall and slender wall, the design force will be differently determined, and this can be automatically considered in the program as well. So the calculated design force, as you can see in the table, those results already reflect those rules to satisfy the capacity design. For the column, the results can be checked the samely. So for the graphical results, we can check for all the design force and capacity in this one sheet. Especially in the column design, we use the PM interaction curve to determine the resistance of the column. So you can check the interaction curve in the report as well. We can separately check the 3D PM interaction curve here. And also detailed report is provided as well. After performing the capacity design, we may want to know if the capacity design rule is satisfied or not. As you have seen, all the results has been marked as OK, which means all the results satisfied the capacity design rule. For the columns also, all the results were OK. And also we can check the joint ratio as well. So we can check each different joint. For the resistance summation between the joints, we can check it. So summation between the beam's resistance and column's resistance for each different joint. If we go to design and strong kernel with beam and strong kernel with beam ratio, we can specify the acceptance limit. I will check all the joints. Then we can see the ratio for each different joint. This shows the ratio between the summation of beam's resistance and column's resistance. So ratio should be larger than 1.3 as we specified in the dialog box here. So we can see all the joints satisfy this rule. If we select this option, acceptance limit, and click apply, it will show us only the joint which do not satisfy this limitation. If I change the value, we can see only those points do not satisfy the ratio 2.1, 2.0. Okay, let's move to the seismic design for the existing building. For the existing building, some of the procedure is the same and some of the procedure is different. Firstly, for the performance requirement and determine the knowledge level, and seismic action and combination are the same. Then perform the seismic analysis and check the safety verification. Finally, the engineer will decide if the intervention is required or not. So let's start with the performance requirement. For the performance requirement, it has different 3 steps, different from the new building. Near collapse, significant damage, and damage limitation. As you can see, it has different return period of the seismic load. For the near collapse NC, it is the structure is near collapse and would probably not survive another earthquake. And non-structural components have collapsed, and also structural component is nearly collapsed. For the significant damage, it is the status that structure is significantly damaged and it would be uneconomic to repair, as you can see here. So no structural components are also damaged. And the other step is DL, damage limitation. This step is structure is only lightly damaged and with the structural elements prevented from the significant yielding and retaining their strength and stiffness properties. So that is the damage limitation. So we can determine the performance requirement based on those three. And in order to satisfy this requirement, we will have the limitation, which is the compliance criteria. For the NC level, ductile and brittle will be differently checked for the deformation, and brittle is for strength. For the SD level, also you can check it here, and DL level as well. And after determining the performance requirement, next step is knowledge level, which was not displayed in the new buildings. For the knowledge level, in order to choose the proper analysis and confidence factor, knowledge level needs to be defined, since it is the existing building. So KL1 is the limited knowledge, which means we are not really familiar with the strengths or the capacity of that building. And KL2 is normal knowledge, and KL3 is full knowledge, which would be mostly similar to the new building. And factors determining the appropriate knowledge level is geometry and details, and also materials, as you can see in this table. After determining those knowledge level, and then we can choose the seismic action and load combination. This part is same as the new building. After that, we will perform the seismic design. For the seismic design, as we checked, it has 4 different types of the analysis method. Among those, we will see the details about the pushover analysis. Why pushover analysis is required? We can check in this slide. Firstly, to verify or revise the overstrength ratio value, which is this. This is the ratio between the ultimate strength and the first hinge formed strengths ratio. And also, by the pushover analysis, we can estimate the expected plastic mechanism and also distribution of damage, and also to access the structural performance of existing or retrofitting buildings, and also as an ultimate to the design based on linear elastic analysis, which is used for the behavior factor. For those purposes, we need to perform the pushover analysis. This shows the procedure in MIDAS, which step is required for the pushover analysis. Firstly, we will define the pushover global control and define the pushover load and hinge property, and then assigning them into elements, and perform the analysis and check the target displacement, and then also hinge status can be checked. Finally, we can do the safety verification as well. So let's see the program. This is the stat model for our pushover analysis. One of the useful function in MIDAS is task pane. Using this task pane, program will show you required step, as you can see, and also related post-processor can be checked in the list. So for the advanced analysis, such as pushover analysis or nonlinear time history and material nonlinear analysis, using the task pane, we can easily find out the related features and results as well. So I will use this task pane for the pushover analysis. Firstly, define the global contour. For the global contour, we specify the initial load of pushover analysis, dead and live with certain factor. Also, in the pushover, in order to neglect this pushover analysis, we can specify the seismic elements group as well. And some other nonlinear analysis option can be specified here. Once we enter the corresponding data, the arrow changes to this V mark. We can easily recognize which data has been entered and which is not. And define the pushover load case. Specify the number of steps. And we will use the initial load, and p-delta analysis can be considered. Pushover analysis incremental method is two. One is load control, the other one is displacement control. We will use the displacement control with specifying the master node here and specify the maximum displacement. And we can select the load pattern among uniform acceleration or mode shape or static load. If we select the static load, it is just specifying the direction of the load. So I will use the static load, x direction. Okay. Then define the hinge properties. MIDAS provides the various hinge types such as Eurocode, FIMA, trilinear, and bilinear. So I will use the Eurocode hinge type. If we click this button, property, we can see the detailed properties here. And also we can change the curve by the ratio in this table. I will use the default values for the beam, also for column. For column, we can use the PM interaction. So yield status will be determined based on those PM interaction relation, axial and moment relations. Okay. And also for walls, we can select the wall type, membrane or plate. If the membrane is selected, which means it will not have the out of plane stiffness. If the plate is selected, it will have the out of plane stiffness. So I will use the membrane type as our structure is 2D. Also, it will use the PM interaction. Okay. After define the pushover hinge properties, and then we will assign the hinge. Firstly, for walls, select the walls and click apply. We can assign hinge here, or using drag and drop, we can easily enter the hinges as well. Select the beam element and drag and drop from the tree menu. Hinge has been assigned here. Samely for the columns. Select desired element and drag and drop. Once we assign the hinge, you can see the color is changed from blue to black color. Black color means the property has been assigned to certain element. Then a required step has been done, so let's perform the pushover analysis. Then we can see the pushover curve. So we can see the pushover curve, and in order to see the target displacement, by selecting and specifying the design spectrum, the program will automatically calculate the target displacement for the DL, SD, and C that we checked the required step for the existing building. Also, we can change those spectrum value as well. If we change it and clicking draw, target displacement is recalculated. Those calculations can be checked in this table below, as well as the text output, as you can see here. So use the parameter here and also check the required steps here. After checking the pushover curve and for the hinge status, we can also check for the moment hinge. We can see how hinge is progressed for each different steps. And for the shear hinge, we can also check it for different steps. Okay. And finally, we can do the safety verification. Also go to the task pane, safety verification table. Show all elements. We can specify the step for the demand, which is contain the analysis results. And based on this selected demand, the capacity will be calculated and displayed in this table. So we can check the brittle mechanism and ductile mechanism. Ductile mechanism is checked based on the rotation, and brittle mechanism is checked based on the resistance. So program will compare between the demand value and capacity. Then OK or NG would be determined. If the safety verification is not satisfied, it will be displayed as NG, with the red text, as you can see here. So using MIDAS, we can also perform pushover analysis, and safety verification is also provided. And the next one is base isolator and dampers. MIDAS also provides the base isolator and dampers to perform the geometric nonlinear analysis. The characteristic of the well-designed seismic isolation system is shown as below. Flexibility to increase the period of vibration and reduce force response. And energy dissipation to control the isolation system displacement. and rigidity under low load level such as wind and minor earthquake. So for those purposes, we need to have the isolators. Firstly, for the isolator, MIDAS provides two different types. First one is lead lava bearing isolator. The other one is friction pendulum system isolator. Using the general link, we can specify those isolators here. For the dampers, we also have the damper for the viscous elastic and hysteretic system damper. As you can see the picture for the viscoelastic and the hysteretic in the third picture. For the viscoelastic damper, we have three different types: Maxwell model, Kelvin model, and combination of Maxwell and Kelvin. So you can select among those three for the viscoelastic. I will show you using the program how to perform the boundary nonlinear analysis. I will use, in order to reduce the time, I will use the model file which already completed for the modeling. This simple model, we entered the isolator at the bottom of the column using the general link. You can see here. Each bottom of the column we entered the general link. Some of them we entered as the friction pendulum, and some of them we entered the lead lava bearing for just our test. The property, nonlinear property, can be specified in this dialog box. Stiffness, friction coefficient, and some other values can be entered here. After defining this general link, and then time history data would be entered. In order to perform the boundary nonlinear analysis, we need to have the nonlinear model and specify the end time and time increment. And the damping ratio for this structure is entered as only one value. So as 5% of the damping ratio. After defining it, you can see there is three different time forcing functions. Firstly, for the seismic load, we can use the database in the program. It provides the various earthquake acceleration records. So we will select L-central for the transverse direction and as well as the horizontal direction. Also for the horizontal direction, L-central earthquake records. The other one is used for the self-weight. Since the self-weight should be entered first before applying this seismic load, that L-central, transverse, and horizontal. So this time function is used. So during this time, which is the 2.5 sec, the self-weight will be entered first, and then after 5 minutes, 5 seconds, the earthquake would be entered. In order to see this, we can see this squaring node is arrival time is 5 sec, which means after the self-wait, and then after the 5 second, then this squaring node is entered. And for the self-wait, we use the dead and live with the scale factor. And this arrival time is 0 seconds. So it means seismic node is entered first from the beginning of this time length. And then after 5 seconds, then a squaring node is entered here. After defining those data, so that's all we need to specify. Then we can perform the analysis. Analysis is completed now. And let's see the results. For the results, time history related results, we can go here and let's check the displacement with the various time. We can check it with the animation. So displacement can be checked here with this legend. With the different time step, we can also specify the certain time to check the displacement as well. So by selecting it from this combo box or in this graph, we can see different displacement of the structure. It's same for the velocity and acceleration. And also we can check the time history graph. Firstly, for the node number 1 and 4, which is this node at the first floor and this node. Those two nodes, we can check the displacement in x direction. Let's compare it to check how different between those two different nodes displacement. So enter those two with the time domain. So we can see this red line represents the first story's node, and this green line represents the third story's node. You can see there is no many change difference between two. By entering the isolator, this difference can be significantly reduced. And also, let's check the historical curve for our isolators. For this, I will try to check the isolator which is in here. Let's check the historical curve of this isolator, which is 19.4 and number 1 nodes. So check the shear force, and the horizontal axis would be the transy direction. So historical curve can be checked, as you can see here. Each different element or each different general link, we can check those historical curve. For your information, for the general curve that we checked the displacement, by right-clicking, we can change the graph to the frequency domain as well. So we can see the frequency domain, and it can be changes between time domain, frequency domain. So this shows the historical curve of the isolator, and this graph we just checked. This shows the comparison without isolator and with isolator for exactly the same building. So without isolator, if we check this time history curve, the frequency can be reduced after entering the isolator. You can see the changes between those two graphs. Also, period has been increased from 1.0 to 1.7. Okay, let's move to the mass and damping ratio. MIDAS provides the various functions to define the mass. So for the mass, we provide the nodal mass, flow diaphragm mass, load to mass, consistent mass, and self-weight to mass. For the generally, if we go to the structural type dialog box, we can select between the lumped mass and consistent mass. In calculating the inertial force in this number 1 point, the acceleration of the point 2 can be taken into account if we select the consistent mass, because it also considers the number 2's the movement, such as the U2, V2, and zeta 2. But if we select the lumped mass, it will have only diagonal matrix, so it would be independent for those two nodes. So we can select between those two mass type. For the damping ratio, we have 3 different methods to define the damping ratio. Firstly, the modal that we used during the model file that we just checked. So we can specify the damping ratio for different modes directly here. Or the other way is using Rayleigh damping. So damping ratio will be calculated proportional to the stiffness matrix and also mass matrix as checked in this equation. And the other way is strain energy proportional. This one can be used for when model file contains more than 2 different material. So we can specify the structural group, damping group, and then differently assigning the damping ratio for different materials. Modal analysis. MIDAS provides the 2 different type of the modal analysis. One is eigenvectors, the other one is Ritz vector. And also in the eigenvector, we can select subspace iteration and Lanczos. If we use the Lanczos, we can perform the analysis for the complex model faster. Finally, the fiber analysis. Fiber analysis can be used for the frame element. Normally if we use just the beam element, we are not able to check the stress distribution or cracks inside of the section, but by performing the fiber analysis, we can see those stress distribution and crack occurrence. So by defining the reinforcement and concrete, also we can define the stress strain curve. MIDAS provides the various database for those, such as Kent Park model and so on. And by defining those curves, we can check the stresses and cracks inside of the cross section. Okay, so that's all for today's topic. If you have any questions so far, please let us know via questions window. First question is related to the pushover analysis, hinge formed in the wall. For the wall beam, similarly, if we assign the shear hinge, it is assigned to the center of the element. And if we assign the moment hinge, it can be assigned to each end, I or j end. So for the moment hinge, if we select moment hinge, the hinge can be checked between those 2 points, I and j end, not the 4 point. This is also related to the property of our wall element. Our wall element would have the very stiffened beam at the top and bottom, and it is connected to one beam. Internally, it is provided like this. So due to this property, we enter the hinge to I and j end for the moment hinge. But the shear hinge, I just mentioned, hinge can be checked in the center of each element. So shear hinge is entered to the center. there is another building. If we can perform the inelastic time history analysis for the steel and masonry material, to perform inelastic time history analysis, firstly, we define the inelastic hinges to the element, which is this function, the inelastic hinge property, and clicking it. Firstly, RC steel, SRC, we can perform those. All user-defined material we can perform. So in this case, so for the elements, we can perform steel, RC, and SRC type. Also, using the user-defined, it would be possible for using the masonry materials as well. And the other question is about civil and gen. MIDAS civil and MIDAS gen is different program. MIDAS civil is for the bridge engineering program, and MIDAS gen is for the building engineering program. The general interface is the same between gen and civil, but MIDAS civil has more features, useful features for the bridge, such as the advanced bridge wizard, and MIDAS gen is have useful features for the building, like story-related results. So it is separate program. You can check more details in our homepage, en.midasuser.com. And the question about what is the difference between the inelastic time history and nonlinear. The question is about the difference between the time history, linear and nonlinear, and inelastic time history. The nonlinear time history is the inelastic time history. And so when you check the model, we checked the geometric nonlinear analysis, which means the structural will be considered as linear. So we didn't assign any hinge. And we only consider the nonlinearity in the isolator, that is the geometric nonlinear. And the other one is time history inelastic nonlinear, that is assigning the hinge to the element, that assigning inelastic hinges, and check the hinge formed during the time, that is the inelastic time history analysis. And the other question is about the floor diaphragm and the eccentricity. If you the usage is a little bit different for the static seismic load and response spectrum load. Firstly, for the static seismic load, it can be specified for different floors in here. So if you have different eccentricity for each floor, it can be specified in this table for the static seismic load. However, if you are using the response spectrum analysis for the seismic load, let me open the model. In this case, when you specify the response spectrum load case, when we're using the accidental eccentricity, we can also specify the different eccentricity for each different floors in here. So that is possible for the entering different eccentricity for each different floors. Another question is about the construction stage analysis. So in this dialog box, we can specify the element group, and by activating them for each different stage, we can perform the construction stage analysis. Apart from those definition, also we provide the time-dependent material, so we can fully consider them during the construction stage analysis. Yeah, so during the construction stage, we can change the boundaries as well. So the previously defined boundaries can be inactivated and new boundary can be assigned in the new different stages. So it's possible to changing the boundaries, like from hinge to fix is possible. So if there is no more question, I would like to close today's webinar. Thank you very much for attending today's webinar. And if you have any further question, you can send email to us. esupport@midasuser.com. Thank you very much.